Hello and welcome to the fifth lab of wireless communication and networking. And since today there was a problem in the Zoom class, so I am recording this video offline for you, and I'll upload it to your lecture on iClass. I will also put the restrictions on the watch time, so you have to go through all the video. And if you miss the video, you may miss also your attendance. So please watch all the video till the end. So we have been studying this end-to-end communication system, and today's lab we will be covering the modulation part, and then transmission using the Awgn channel, and also we will try to cover the receiver filter. So here is the big picture. We saw the analog source, which was our message generation. So the message generation can be anything, and any source coming from the, for example, microphone or your camera or any other thing. And that analog source is going for the sampling process. And after the sampling process, we were quantizing that, and the quantization was following by the encoding process. So we have done everything till encoding, and today's lab we will be doing the modulation, then transmission through the Awgn channel, and then the receiving filter. So let's get started. Before I'm going to start with the modulation, first let me go through the all the processes that we have done before, so that you have some recap of all the previous code. And since this is also the continuation, if I'm doing the modulation part, you have to also remember what we have done in the previous part, like for example lab 3 or lab 4. So we will be still using those variables, and to understand what those variables were doing, then let me go through it roughly, and then we will move forward. So firstly, we defined the modulating frequency. I am emphasizing on this modulating frequency because we will need to talk about this today. So FM is the modulating frequency, and that modulating frequency was composed of several harmonics and also some amplitudes. So the harmonics means that there were several frequency terms, yeah. There were several frequency terms, and also the amplitude, several amplitudes. So the purpose was to make the signal looks like a bit random. It is not random, though it's repeating itself, but we took the part of their signal, and that part of the signal was looking as random, and that's why we used the different frequencies and different amplitude. And then we defined the system sampling frequency. So the system sampling frequency was the source analog frequency, and also then we defined the sampling rate, the consecutive difference between two samples, two frequency, this system sampling frequency points. So actually this was your analog frequency, and the point between the interpoint distance was the sampling rate. And then we visualized two two cycles of that signal, and finally we use this we use the message signal, and we use the sinusoidal addition in the form of Fourier series to make the random kind of sinusoidal signal by summing up all the amplitude and frequency terms. And then we use the sampling part. So in the sampling, as I told you, we have to track for the highest frequency component. I will show you in the slides now. And after the when we see the maximum frequency, our sampling should be happening a couple of times more than maximum sampling frequency available in the signal. And then that's why we have chosen this number as 5. So we choose 5 and the maximum harmonic and the frequency component there. So the modulating frequency multiplied by the maximum of the harmonic, which is probably 2. Yeah, 2 is the maximum number. So that is multiplied, and then 5 times of that is your sampling frequency. And here we sampled the frequency, and then we plot it. and then we also quantized it. So we knew that what number of samples we have. So analogously we can say that the sampling is something you are doing with the signal on the x-axis, and quantization you are also identifying the point on the y-axis. So we defined four quantile intervals, and those quantile intervals were then also quantized there, and then we plotted it here. And once we had the quantization there, so every position of the sample signal was defined after the quantization process, but it was still analog. So to convert it into digitized form, we perform some encoding, and we use the binary to decimal built-in MATLAB function to you encode that every point of the signal, and we use 4 bits of the uh, decimals, 4 bits, and we converted each decimal point into 4 bits, and the leftmost bit was MSB. And then again we saw everything till this point. Let me also give you a review on the pad, and then we will start with the modulation and the today's work. So the first part was we generated a signal. And what kind of signal we had generated? So we had different harmonics, uh, and also we have different amplitude. So what is harmonics here? Let's say my y-axis is the amplitude, and my x-axis shows you the time. So our signal is, so far our signal is time domain signal. I'll also show you today. We will also see some frequency domain signal and also converting to the frequency domain. So I'll show you that later, but all the signal we are dealing with so far, they are time domain. So we generated a signal. So we had, for example, fi harmonic we have defined, for example, 1, 0.5, and 2, and 1. These were the harmonic for us. So 1 harmonic means that the number of cycles are completed at 1 second. 0.5 means that the number of cycles are completed at 0.5 second. 2 means that 2 cycles are completed per second. And 1 means again the number of cycles are completed per second. So this is how we took the Fourier series of those signals. So all are added up, and we got some signal which looks somehow random. It was not completely random, but the signal was looking somehow random. So after generating this signal, then what was the next point? The next point was we cannot transmit it because there will be lot of informations like that, and we don't have to convey all those informations. So we also have to use the resources efficiently. For that reason we did some sampling. So how did we do the sampling? For the sampling part, we were looking for the maximum frequency component available. So if we look at this part, the harmonic part, the maximum frequency component, for example, was this one. So we have to take care of only checking the maximum frequency component. Let's say this is the maximum frequency component available here, and after seeing that maximum frequency component available, we have to sample that maximum frequency by couple of times more than that. And why? What is the reason of couple of time more than that? Even for example, you are doing it by one time. So this is the maximum frequency component available. You did it this, and then here, and then maybe, so this will be repeated periodically at regular interval of time. So the distance will be similar for all of them. So if you are recovering, then this will not be what you have transmitted. That this will not be equal to that. So you have to transmit it uh, meaningful. You have to transmit meaningful information, which means that you not only have to save the resources, but you also have to send all the component of that signal. So at least it should be 2 times. It should be more than 2 times. So if you choose, for example, 5 times of the maximum frequency component available, it means that you are obeying the Nyquist criteria. So the Nyquist criteria is related to the sampling of the signal. So it's required for this signal to properly sample it so that there is no aliasing problem, and the signal is recovered at the correct way when it is received. So you have to sample the signal at proper points, and then that kind of sampling we did previously that we saw in the sampling lab. Now, after doing the sampling is something like you can see all the signal in x-axis. For example, you can say that this one is sampled here, this one was sampled here, and this one was sampled there. And if you recall, we had skipped three of the original signal uh, the original signal points, and then we were choosing the fourth point. Again, we skipped three other signal points, and then we choose the 4 points. So we were choosing our signal like 1/4 of every point. Not every, we are not choosing every point, but we were choosing 1/4 of every point. So this is not the exact solution, but just to demonstrate you how it works. You should be sampling at such a way that it should obey the Nyquist criteria. Now you already sampled the signal, and as you know that you have the x-axis information of all the signal. Now, what is the next step to be done? The next step is, for example, this is, I also have to mention that your signal was like this. Some part of your signal was positive and part of your signal was negative. So sorry about that. The time axis is here, for example, and your signal was looking like that. And now, let's say that I am uh, choosing the quantization point. So the quantization, for the quantization point, we defined two intervals. We saw that what is the maximum and what is the minimum, and that whole interval we called it, this is our quantization interval. So the interval between the maximum point and the maximum minimum point, and then we further defined some level for that. I think we defined 4 levels for it. So 1, 2, 3, 4, we defined 4 levels for it. And then we were starting from this level and we were moving to the upper level, and we were checking which signal is contained in the first level, which signal is contained in the second level, which signal points are contained in the third level, and which signal points are contained in the fourth level. So if you look at here, any signal points that are contained in this level, they will be located this quantile interval. For example, this one is this one, and also this one. So they all these points will be assigned this quantile interval. And then there are plenty of other points which is locating in this region, and it belongs to the second quantile interval. So all the quantile points will be allotted like this point. So this is the all the quantile interval, they will be looking like that. So if you see that this is the original quantile interval, and there is some difference between the original point locating and also the quantization that is done by you, and that thing is called quantization error. That is called the quantization error. So your quantization error can be reduced by increasing the number of levels, and if you are increasing the number of levels, you are again you have to pay it in the form of overheads. So you don't want to have too much levels, because too much level means that you will have some of the levels which doesn't contain any kind of points, data points, and those quantile intervals will be going wasted, and some of the points will be there which are containing the points. So you have to wisely choose this quantile interval in such a way that you have minimum quantization error. There will always be this quantization error. You cannot make it zero, but you can bring it to a minimum value. And likewise, you will do the quantization for this level and also for this level. So in our case, we just defined 4 quantization interval, and we just we also defined kind of y-axis also for your signal. Now, after this point, as I told you that part of your signal is lying below 0 and part is lying above 0. So let me plot that signal again from a clean view. So this was your original signal, for example, something like maybe like this. So part of the signal, and these were your defined sampled and quantile interval. So here you have everything. Now to this is the, for example, the minus 5 volt, and this was the plus 5 volt. The maximum was plus 5 volt and the minimum was minus 5 volt. Now to do the encoding process, what do you need for the encoding process? You don't like to have the negative values because negative values are different to calculate, so we do some tweaking with that signal. And how do we do that? We just subtract this minimum of signal from every point. So once you do that, for example, minus 5 is subtracted from 0, so it will be 0 minus into minus 5, so it will become plus 5. So the 0 level will raise from here to here, and this level was raised to 10 point, and this level will raise to the 0 point, because minus 5 minus into minus 5 is equal to 0. So your other signal will looks like maybe like this. I hope so. Yeah, the red one is your new signal because you wanted to get rid of it, and to get rid of that, now you have the minimum 0 and the maximum is 10. So somehow your new signal will looks like this. uh, I hope like this. So sorry, not below this line, otherwise it will become 0. Now every point is now positive, right? So after you are having all those quantized interval, and they were also shifted upwards so that to have it a positive values, you are having something like this. And after doing this, you just choose every point like this point, and you converted this into equivalent binary value. For example, if it was 3, so you made it 0011, and if it was 5, you made it 0101, and if it was anything, for example, it was 2, so you made it 0010. If it was 10, you made it 1010, something like that. So every point contained in that particular position, firstly, what happened? Firstly, the position was defined. How the position was defined? By doing sampling and quantization. And after doing this, you converted into a binary form, the equivalent binary form. So far we are here and we have all the signal ready till the binary form. So let's see what is happening to what can we further do with this signal. We have to now modulate it. So to modulate it, I will briefly give you some review why do we need the modulation and how we are going to deal with this point. So the modulation is the process of imposing the signal contained in a lower frequency signal onto a higher frequency signal. So if you have a signal which is this one, and if you remember, I also already told you that it is my FM. I will talk about this. So my FM was 1 kilohertz, right? Some thing like that. For example, this is my input signal, and the frequency of this one is 1 kilohertz or 1000 hertz. So this is the signal. Why do I need modulation? So if you don't want to do the modulation and you want to transmit it, you need a very huge antenna, because the length of antenna is proportional to the lambda by 2 or lambda by 4, or it depends. So it's the dimension of antenna which is depending upon the wavelength of the signal. And what is wavelength? Wavelength is inversely proportional to the frequency. And what is frequency here? Frequency here is equal to 1 kilohertz. So if we compute this one, the speed of light is 3 into 10 raised to power 8 meter per second, and the frequency here is 1000 hertz. So it seems like your wavelength is 3 and 5 zeros, right? Yeah, almost this much, 300,000 meter. So this is your wavelength. So it seems like even if you take half of this, which means that you need this much dimension, this much of antenna. Is it practical? Which means like 150 kilometer of antenna. No, it's not, right? So you have to do some modulation, and to do the modulation you have to use the high frequency component. So for example, we are using FC, and let's say we are using 1 megahertz. 1 megahertz mean that 10 raised to power 6 hertz, or even more than that. For example, for Wi-Fi signal you are using 2.4 gigahertz, or even for your microwave you are using 2.4 gigahertz. And do you know what is the why we are using the 2.4 gigahertz band so frequently? For example, your Bluetooth is using the 2.4 gigahertz, or your Wi-Fi is using this 2.4 gigahertz. Why? The reason is this 2.4 gigahertz is a license free band. So what does it mean? So every frequency on the earth has some value, and it's not for free. There is an organization which is called the ITU. I'll just briefly talk about it. It's out of the scope of this lab, but I just want to talk about it. And the ITU, International Telecommunication Unit, they are basically um, dividing the frequency with respect to region. For example, Far East region will have some different band of frequency allocated to them, and then they will have different standard in the European region. So once they allocate a part of for each country, for example, we are talking about the Korea here, they have this much of band of frequency defined, and then for example this much of band are used for the communication purpose. All the frequencies are used for the communication purpose, right? So frequency band mean that the roads, it's kind of roads, so roads for the transportation system, and they should not be conflicting with each other. So for example, for the FM frequency, if you are using something for FM, and there are plenty of companies who are using FM, who are broadcasting on FM, right? Even the FM people have to purchase those band. For example, this is FM 106, then there is FM 105, FM 103 megahertz. So the FM is ranging from 8 megahertz to 108 megahertz. So once this FM is purchased by, for example, A person, the B person cannot use that band because A already paid for it. And if B is using that same band, it means that two frequencies will be interfering with each other and none of them will be working, because the same road is used for two cars. One car is here, two cars is here, and this road is built for only one road. So if two cars are running on the small road, they will collapse, they will collide with each other, and they will get damaged. So the same thing is happening here. So if you have one frequency there, the license frequency means that those frequencies have been registered by some person or some company, and those frequency cannot be used by the other person. So if some other person need this that bands, they have to purchase other than that frequency. For example, this one band, so they have to purchase 105 megahertz or 103 megahertz. So in that way they are not, for example, if someone is using broadcasting on 106 megahertz, the other person, the B, if he is broadcasting on 105 megahertz, they will not be conflicting. Why? Because this has been licensed, this is purchased by this one, and the other frequency band has been purchased by the this one, right? And then this whole country is purchasing from this one, this ITU, which as I was talking about, and this is the super body who is managing all these frequency stuff, right? So this is how it works. The main band is purchased from here to here, and then from here they are further selling it, and from here they are further selling it, and then from there the one person cannot use the other frequency band. Now let's come back to this 2.4 gigahertz. Why do we see the 2.4 gigahertz so frequently? Because this is the license free band. You can use it for your experimental purpose, or you can use it for the Wi-Fi purpose, or you can use it for the other, for example, Bluetooth purpose. And all these frequencies you don't have to purchase, they are license free band, and that's why we like to use it so frequently. Like microwave and every device is using this frequency. And it's not so now you will be thinking, if we have, I told you this story, right? Like A is using 106 but B cannot use that 106 because they will be colliding. Then we have only 2.4 gigahertz, and if there are plenty, for example, if you take the example of Enha University, you will be seeing lot of Wi-Fi devices, right? Like plenty of Wi-Fi devices are there. Then why don't they interfere? Because I told you that it's like only 2.4 gigahertz. Now there is another answer for this. All the 2.4 gigahertz spectrum has been divided into subbands or subchannels. We call it channel, and there are almost 13 channels there. For example, 1, 2, 3, and up to 13 channel there. So, in for example, in a room A, there is a room A which has a Wi-Fi device. Sorry, the Wi-Fi is icon as this, and then there is another room which is room B, and it also has a Wi-Fi device, and it is also using this 2.4 gigahertz. So there is it is using some CDMA technique, and it is, I will just explain in a simple words, that if one channel is used by this one, B is sensing that since this channel is busy, so I should not pick this one channel, but I should pick up the other channel, which is the channel number 2. And if the channel number 2 is occupied by this one, and the channel occupied 1 is occupied by this one, and then there is another Wi-Fi in the same range, and it also wants to transmit the data, it will again scan for all the available channels, and it will see that this is busy, but this one is free. So why don't I use this one? So then this one is used by the third Wi-Fi, and if there is fourth Wi-Fi, it will check for the other one, and it will keep using the fourth number channel. So in this way, the channels are well utilized by sensing whether the medium is busy or not. If the medium is busy, that one channel is not used, and the alternative channel is used for its transmission, right? That's why we likes this 2.4 gigahertz band so much. And why was the story here? How does the story started? 2.4 gigahertz, if we see that lambda is equal to for example, what is the dimension of antenna that might be needed for 2.4 gigahertz devices? So here you can see that lambda is equal to C over F. C is 3 into 10 is power 8 meter per second, and divided by F is how much? 2.4, and into 10 is power 9. So if we see, it will gives us 0.3 meter. And if we see like the proportion of this, for example, lambda over 4, so we already have a very small, almost 1 foot of the wavelength here. So if you divide it by 4, means that this much times 1, 2, 3, 4, 4 times this much of antenna you need to transmit it. That's why the Wi-Fi transmitter is so small. You have a very small transmitter there. That antenna is enough, because the frequency is so high that the proportion of the size of antenna is very small, and that antenna is enough to transmit your signal. So this was all about the modulation scheme. That's why we need the modulation. And why we need the modulation? So that to increase this frequency. And to increase this frequency means that then we need a small size of antenna. And that small size of antenna is sufficient to transmit the same information with low power. So after the modulation, we have an other thing we have to explain, that is Awgn channel. Okay, I'll just show you what the big picture is. Now you have a house, for example, this is a building, building. Okay, and here is the mobile tower on the top of that building, and then there is a house which is almost 1 kilometer away from here. almost 1 kilometer away. And then that house, for example, this is a house, and then there is a person inside the house who is laying in the bed and he is using his mobile. And now how does this frequency from this building is reaching to that person? For example, there are trees here, and then there are roads and some vehicles are there, and then there is also a lot of stuff, so people are moving here. Yeah, then other guy is here. Yeah, some these dancing guys are there. And now this signal is transmitted. For example, this signal is transmitted. So once this signal is transmitted, there is, for example, the other building here. It is striking off this building and then this one, and the leaves will further reflect, scatters the signal like this, and finally it will maybe strike with the edge of the building. It will diffract like this, and finally with reflecting like this, and finally some portion of this signal is received here. But this signal, this portion of signal was not received from a single path. If it was a single path, then it was okay, but we have plenty of other ways. For example, striking off the road, then that building, then that this person, this one tree, again this building, and finally to that person, and then again to that person using this vehicle, and lot of replicas of the same signals are reaching to this person. So if this signal is this one, and if the other signal reaching, for example, this one signal is this one, and if the other signal is this one, if you see this one is out of phase to this one, they will cancel each other. But this one and this one, they are of the same phase though, so they will add up. This is called fading. So fading is happening to the signal. Sometimes they are constructively added, and constructively added mean that it will gives you a full very huge signal. And sometimes they are constructively added. Constructively added means that they will either cancel each other or they will degrade the quality of the signal. And finally, the signal that you had transmitted, it was like, for example, a very nice signal like this, but when you receive it, it will be something like that, because of the various channel degrading phenomena. So why we are using the AWGN channel? We are using the AWGN channel because it is a simulation model that contains all these channel degrading phenomena, and all those kind of noises or distortion related to this channel are there. So these signals are then when this signal is received, it will contain tremendous amount of noises there. And why it is called white? Because the level of the noise will be same. It is same as the white color, and the white color has the same reflection. That's why it is termed as white. And it is Gaussian because it has the Gaussian shape with zero mean and some standard deviation here. That's why it has the Gaussian shaped. So AWGN signal is reaching to the signal, the original signal reaching with the with the noise factor, or with the noise, is looking somehow like this. So you transmitted this clean signal, but when it received with noises, and those noises basically corrupted your signal. They are trying to corrupt your signal. Now it depends on how much is the signal to noise ratio there. So what is the signal to noise ratio? Signal to noise ratio is the signal power divided by the noise power. So if the noise power is huge than the signal power, which means that the denominator term is huge and the numerator term, which is the desired term, is less, it will further deteriorate your signal. It will further corrupt your signal. So it means that these terms are very huge, like this. The noise is very huge. But if your signal to noise ratio is high, it means that your signal power is huge and your noise power is less. In that case, if this was your signal to noise ratio will be huge, which means that you have lower chance of your signal to be get corrupted from the noise. So what is the solution here? When your signal is reached at your home or the place where you are sleeping or you are using your device, and the signal coming from different sources, and when it reaches to your smartphone or your receiving device, it contains the AWGN noise. So that noise has to be removed. So to remove that noise, what is the strategy? We require some filters, and there are a lot of types of filters. I'll just simply explain one of the simplest one. So what is filter? I'll give you what the how the filter works, and then we can we don't have to go deep into filters because filter is a very broad field. So as I told you, your signal, if this was your time domain signal, it was accompanied by some noises, and that noises, the signal then have some SNR, and if the bigger SNR value is better, and if it has low SNR, it means that the noise power was greater. Now, how to remove the black from the red? How to remove the blue from the red? This is your noise. The blue is your noise, and how can we squeeze out this red signal, which is our desired signal? To squeeze out the original signal from that, you need filters, and filtering is not so easy. So one of the good way is to visualize the signal into frequency domain. So as I told you the previously that I'll talk about the frequency domain too, so here is the time I would like to talk. So far we were dealing with the signal in the time domain. So when you want to see the signal in the frequency domain, it means that you want to see that how much frequency component are there. If you see the signal in the time domain, you cannot see the number of components there. As we saw in the previous, we defined 5 harmonics. For example, if I go back to the slide, we have seen that, or even further. So I have used 1, 0.5, 2, and 1. I used 4 harmonics there, and out of these 4 harmonics, I cannot see which frequency is which one, right? I cannot guess it from the time domain. But if you convert the same signal into frequency domain, it will shows you clearly that this one harmonic is, this is 1 harmonic, this is 0.5 harmonic, this is the 2 harmonic, and this is again the 1 harmonic. So your signal is contained 4 type of signal, which contain this much, this and this frequencies. So this is why we need to see also the signal in the frequency domain. Although nothing happens, like it is kind of mirror. You see your face in the mirror, but in a different from a different angle. So the main thing is similar. The data is similar. The data is still there. The data is still like the signal you have transmitted, but you want to visualize it in other domains so that you can further analyze the signal. So if we come here back to this topic here, we have to see this signal in the frequency domain. To see it in the frequency domain, we have to see how much frequency components are there. So this is the frequency domain. So from the time domain, we will convert the signal into the frequency domain. And do you know in mathematics what we do for that? We do the Fourier transform. Fourier transform. By taking the Fourier transform, it means that you are converting the signal from the time domain into the frequency domain. So if you are in future doing some image processing or signal processing, you will be frequently seeing this Fourier transform and this stuff. So what is the purpose of this one? We want to see the noise terms, and we also want to see the desired frequency terms, which is your fundamental frequency. The original frequency is called fundamental frequency, and the harmonics terms, they are called the noise terms. So once you convert it into this frequency domain, you will see that this is your one frequency, maybe this is your fundamental frequency, and then there will be other frequencies and maybe a lot of frequencies. If you have more noises, different replica of the frequencies were and different Doppler shifts, and it will keep changing your frequency. And your received signal, as I told you, it is not made from a signal frequency, but different frequency from different sides come, they add up, and they gives you some fading, some different frequency component. So each will making some different frequency terms. These noise will have some different frequency terms, right? And then you will have this frequency. So if you clearly observe this signal, your original, the red one has a very low frequency. It has a low frequency. But if we see the blue one is repeating very high, right? So it has high frequency, which means that all the noise in this case it's not always true because it depends on the system and the transmitter, the receiver, and the noise factors. But just in our example here the noise term is caused by the high frequency. So any high frequency which will be contained there in the frequency domain, we will simply discard it, and we will only keep the frequency which is belonging or very close to the fundamental frequency. And after doing that, if we recover the signal back to the time domain, it will looks very clean, or it will be looking like this. So you can see that before it was very noisy, and after processing it through a filter, your signal has become very clean, although there will be still some noises there, because I told you that very fundamental frequency are the frequency closer to the fundamental frequency, which means that you still have some noise there. So the noise is still there, you cannot eliminate it completely, but still you can recover the best version of the signal. So once you recover this best version of the signal, you will, then we will see in the next lab what can we do with further with this signal to recover our transmitted signal, something which we had transmitted. So let's do it in the MATLAB. And if you had any question related to anything here, you can simply send me an email, and then I'll reply you through email. And if I could not reply clearly on email, then you can ask me in the next lab session. Now I'll start with the modulation part. So we are doing one of the very simplest modulation, and that is the BPSK, or binary phase shift keying. So I'll say that pass band modulation. And for the pass band modulation, firstly, what I told you, I have to define a very huge frequency. So my fundamental frequency, if you see it on the top, it is 1 kilohertz, right? This one. This one is 1 kilohertz. And now I have to define a frequency. Let's say I'm calling it FC, 1E6. So 1E6 means something like 1 and 6 zeros, right? So 1, 2, 3, 4, 5, 6, yeah, they're equivalent, right? So this one, megahertz. So this frequency I'm going to, sorry, not megahertz, this one hertz. And if I don't want to write all the zeros, I will simply write that it is 1 megahertz of frequency. So Fc is my transmitted frequency, and now when I am transmitting it, then I also have to define the sampling frequency for that one. So even my frequency is high, but I have to sample the high frequency too. So for example, I'm saying that nsamp or nsamp, this is 10. So I'll be sampling at 10 times of that. And for the sake of better visualization, I will say that I want to take two cycle of the signal. So I will say that n cyc is equal to 2. So this one, let me first define what is the beta interval. So the beta interval, which I will call TB, is equal to, it is starting from 0. And what is the sampling frequency? It should be this one, and times this one. So the difference of the TB should be the difference between these two. Why this two? Because I don't want to take only one over 1 megahertz, which is one microsecond, but I want to also 10 times of that to obey the Nyquist criteria. So it's almost the same story. And then I will say that I want to visualize 2 cycles. So I am saying that 2 cycles divided by FC. So can you guess what is the frequency now? I'm starting from 0 and I'm going up to 2 and divide by FC. So it clearly says what is my FC? It is 1 megahertz. So what would be the the bit interval. The bit interval is 2 microsecond. Why? Because 2 divided by 1 megahertz, and this megahertz when goes up it will become microsecond, and this 2 is already there, so at the each bit interval is equal to 2 microsecond, right? So within those 2 microsecond I have to transmit one bit. So one bit is transmitted in 2 microsecond, and how much cycles are there? Within 2 microseconds I have 2 cycles. So NYC means that there are 2 cycles, which means that I have one cycle and then another cycles, and those 2 cycles collectively convey one bit. And you already saw how the bits were generated, right? So the bits were generated like that, and then each bit is transmitted one by one, and one bit is transmitted in 2 cycles, and each cycle is 2 microseconds. So it's a pretty simple story. And now I want to transmit the signal. So I'm not very thoroughly explaining this part. I'm just uh, roughly writing it, roughly explaining it, but you have to understand this part, because I believe that you are now good enough to understand how do we make offset and how do we do this stuff. So I'm starting from the zero signal, and then I'm again having this kind of offset. Control C. So by the way, T-tran is our transmitted signal, the signal to be transmitted, right? So I will take this offset again, and then I'm saying that how much bits are do we have here? I don't know. Any number of bits are can be there, but each bit has to be transmitted by how much number of cycles? Two number of cycles. So one bit is transmitted by 2 cycles, so the total number of bits should be multiplied by 2, so we require that much number of bit to be transmitted, right? So let's say, I should not say the bits, because this bits is the vector, right? Or it is an array which contains many bits there. So I should say the size of the bit or the length of bit. So the length of bit means that the size of that bit, and then I will just make it as a numerator and divide by what is my denominator, divide by Fc, because it is starting from 0 and same as this one, but instead of 2 cycles, now I have this much number of bit. So this much number of bit, each bit has to be conveyed by 2 cycles, so that's why I have to divide by 2, which means that each 2 cycles of 2 microsecond should be conveying one bit, right? Plus I'm adding something, and you have to tell me in the next lab. I'll be randomly asking from any person, why did I add this line? I'm adding something here, so I would prefer not to explain it now. So bits -1, but I would ask you in the lab, and then FC word simple. So you have to explain me in the next lab that what was the purpose of adding this extra line here, right? So that this you have to explain me from here to here, okay? And it has some purpose. I deliberately added this one. It has some purpose. So without this, it will not work. Now I will make a modulated signal, and before the modulated signal, sorry, let me call it modulated signal. uh, I want to put everything in this modulated signal, but it should have some size of this one, right? So I will say that it should have zeros inside it before, because I want to uh, fill it with something very blank mean that there are zeros there. And how much zeros should be there? It should be equal to the size of this T transmit, which we already defined here in the line number 70. And after this I will go to the next line. For example, I will put a for loop here, and just not to forget, I will also put an end here, and now I will say everything in the for loop. So for example, I have a variable k and it is starting from 1, and now look at here, I declare this one, right? So the length of every signal should be this much, right? And how much should I go? I should go up to total transmission, so the total size of the signal. So I should also write the length of the total signal. So it will start from 1 and 1 till this bit. So this is the offset between this one. So 1, after this offset, the other. So after 2 microsecond of offset till the end of the signal, it will uh, run for the for loop, right? And I will say something here. So what is my purpose? Since I told you I'm using the very common or very easiest form of the signal, sorry, the modulation, and that modulation is uh, binary phase shift keying. Binary phase shift keying means that if I have a bit 1, I should assign one pattern of the signal to that one, and if I have a bit 2, I should assign a different pattern of that signal. Since I have two cycles which can convey a single bit, so if that single bit is 1, I'm saying that okay, my signal should be cos signal. So the cos signal is always starting from 90 degree, and then it oscillates at regular interval of time. So that 90-degree signal will start, and after completing two cycles, it will be enough to convey my bit number 1. But if it is bit number 0, if it is the else condition, it should start from the minus cos, which means that the cos will start from the minus 90, or it should start from 270 degree. So it should start from the bottom, and then it should complete its two cycles. So each sequence of the bit, for example 1010, each bit will be conveyed by two cycles of 1 microsecond length, and they will be presented like this, either starting from 90 degree for bit number 1, or if it is bit 0, then it will be starting from the 270 degree. So I should put a condition like that. So am saying that if my bits of let's say I'll declare another variable here. Let's say I am saying that L is equal to 1, and I'm saying that if my bit of L, for example the first bit, it is equal to 1, then I would say that my modulated signal mod underscore sig that I already defined here, for example this one, it should contain uh, k colon k plus length. I will just explain you what this thing means, of tb and minus 1 is equal to cos of 2 times pi 2 pi f of t, right? So 2 pi, what is f? F is my fc. What is fc? With this 1 megahertz, that's why we define it here. And what is the bit interval? It is this one, so I also defined it here, control v, right? So my this thing should contain 1, and I'll explain you this thing just in a while. Else I will just copy this thing. Yeah, I'll copy it and I will paste it here, and then it should contain minus cos. So if the any bit is 1, if any bit is 1, it should contain the signal which is cos 2 pi fcftb. But if the signal is 0, then it should contain the reciprocal of that, which is starting from that one. And then I should just finish it. And also, since I'm using this L1, so I should keep incrementing it. L is equal to L plus 1. So I think it's pretty simple. Let me explain you this part. So it's starting from k is equal to 1. So the current index of k, which can be any number here, plus length of tb, which will be this length. So it will be jumping. For example, if this bit, for example, the current bit is 1. So from here to here, I have the tb length, and it has two cycles, and those cycles should be cos 2 pi fc. So it should be starting from the 90 degree. And if that bit is 0, then those two cycles should be starting from the 270 and from the reciprocal side. So this is the whole story now. So I am done with the modulation. This is how my signal is, and why it is called binary phase shift keying, or binary phase shift keying, because it has only two state. Either the signal is plus or it is minus, right? So the signal can be having two signals. There are different types of modulation scheme. For example, QAM. QAM has four. If it is four QAM, it means that you have four quadrant here, right? And each quadrant of each quadrant contains one constellation of the signal. If it is 16 quam, then each quadrant contain 4 constellation of your signal. If it is 32 quam or 64 quam, they are equally divided in those 4 quadrant, and that's why it is called quadrature amplitude modulation. So, phase shift keying or quadrature amplitude modulation, QAM or PSK, they are generally used in nowadays communication system for the modulation purpose. So this is done. The modulation part is done. As I told you, it was the simplest one, and now I'll do the AWGN transmission. So for the AWGN channel, I don't have to do anything because there is a built-in function. Let's say I'm calling it tron underscore signal. So I'm declaring this tron underscore signal for this signal. What is my modulated signal? Which is this one. We just define our modulated signal, and I'm saying that this modulated signal has a signal to noise ratio. So already you know the signal to noise ratio, so I don't have to explain it again. And I'm saying that the signal to noise ratio is 10 dB, which is quite reasonable. It means the signal strength is quite good. And then I'm saying that it should be distorted or it should be corrupted by the AWGN channel. So I will just simply put the AWGN, and the MATLAB knows this function because it is the built-in function of the MATLAB, and it will just take the signal and put some distortion on its phase. So the AWGN is added to this one, and then let me plot the signal, the original signal and also the corrupted signal. So I'm saying that it is the figure number maybe 3. I think I already plotted 2 figures here. So the encoding was figure number 5, so I think it is figure number 6. And the figure number 6, I am plotting it like that. T-tron is my transmitted signal, which is this one. X for the transmission signal. And then what was the transmitted signal at the that side? It was the modulated signal. So this was transmitted before transmission, and then I am saying, let's say I'm just denoting it with the representing it with the blue color and with the dotted line, so something like this. And then I am also doing it, keeping the same axis. We have the x-axis too at the receiver side, so the axis never changes, the x-axis never changes. However, there can be some problem in the y-axis because the amplitude of the signal is distorting when it is traveling, and it can be reduced. So the amplitude always reduced, but the time should be similar as the transmitted one. And then this one signal, so this is the received signal now. And if I look at this one, it should be, let me represent this one as red signal, and let's see how it looks like. So if you don't put the semicolon here, you will see everything. So this was the blue was my transmitted signal, and the red is the received signal. So it is quite corrupted. I want to zoom let me zoom it further, and you can see can you see the red one is the received signal, and the blue one was the transmitted one. So all these are the nice term. It is not, the red one is surpassing the blue one. often, right? So this spikes is extra, this spike is extra, this point is not coming on this one. If this red line, the red color plot, if it was, the red is the received signal with the errors, and if it was overlapping over the blue, then it means that it is a perfect received signal, there was no degradation happened. But here you can see that there is a lot of degradation in the signal, right? Not a lot, because it is not that much. If I reduce this, if I, for example, keep this one as 5, you will see that it will, the awgn channel is corrupted more, and when it is corrupted more, you will see that there will be more degradation in the received signal. And now let me show you how. So with the low signal to noise power means that, can you see the spikes are very aggressive? You can see that there are more spikes there, right? Lot of spikes there. And if you further reduce it, if you further reduce the signal to noise ratio, your signal will become further deteriorated. We don't want to distort our signal that much. That's why we will keep the signal to noise ratio as 10, right? So this is how your transmitted signal was transmitted without noise, and after the noise term, when we edit it, the red one is showing that one. And to not see these things, and they also take some time, you have to put the semicolon here, and also the semicolon here, and also the semicolon here. And you also know how to define the axis, so I will define the axis for them also. Let's say I'm saying that 0 space 3 times of the cycles, so I want to see 3 cycles only. So 3 times of the nyc, sorry, nyc, what was that, ncyc, I think. Yeah, this one. So I should just copy, sorry, command z, command d, and control c, and then from here I will just paste it. So 3 times of the cycles, and then I think I should also divide it by fc, because it is modulated now. If I don't divide it by that one, then the x-axis will become something else, -2 and -2. So now I should be only seeing 3 cycles of my signal. I should not see yeah, 1, 2, 3. So I'm transmitting 2 cycles, so something like that, you can see it. But I am also getting some error, and the error is value must be 1x2. So I think something is wrong. Oh, this one is wrong. So it is starting from -2 to +2. So -2 means that this is okay. Now it is without error. So this is the first, this is called axis limit. Axis limit means that the x-axis should start from 0, and it should show me 3 cycles, and then the y-cycle should start from the -2, and it should goes up to +2. So you can also put the x-axis label there, and you can say that the title, and the title you can say that the transmitted signal and the noise added received signal. So transmitted signal and noise added received signal, and followed by this I can also make some legend means that which one was transmitted and which one was received, so you can clearly distinguish the two. So the first one, which is this one, modulated signal, it was the transmitted one, right? So transmitted. And the second one, which was this one, was this one, it was the received one. This one, sorry, this is the received one. All right, this is done. And then the y-axis, y label, x label is your time, x label is the time, and y label is the axis, sorry, the amplitude. And if I see this again, oh sorry, the spelling is wrong. This is YAB label. So the time axis, it is here. So I'm transmitting 3 cycles, and as I told you, each cycle is 2 microseconds. So first cycle, second cycle, third cycle, right? And so I'm totally seeing 6 cycles. So I'm transmitting a lot of cycles, as you see in the previous lab, but to better visualize, I only showed 3 cycles of that, and you can see that the transmitted signal, the blue, is this one, and the received signal is the red one, right? And if you see it further clearly, you should also put the grid on so that you can compare that how much the difference is there. Okay, so we are done with the modulation part, and we are also done with the AWGN part. So let's come to the tricky part, the receiver filter. So I'll say that the receiver filter. So the receiver filter, firstly I have to express the signal in the form of frequency. So I have to transform the signal from time domain into frequency domain, right? But for that, firstly I have to define the axis. To define the axis, let's say I'm saying that f req is equal to minus. Okay, in the frequency domain, the signal is generally represented from minus limit to plus limit divided by 2. So generally the signal should be starting from 0 till the end, as we shows us in the time domain signal. But when you transform it into frequency domain, it is represented something I'll show you in the figure here, this one. So once you transform the signal into frequency domain, it represents into the from the minus fs by 2 to the plus fs by 2, and there is some symmetry kind of relationship. So anything which is happening from 0 to fs by 2, the same thing is happening from 0 to from minus fs by 2 to 0. So the same thing is happening here. So it is also fine if you only take this part of your signal, or you take this part of the signal, or both. It depends on your application. But in frequency domain, you always express the signal in the form of minus fs by 2 to plus fs by 2. So for that sake, I'm just taking the signal from minus limits to plus limits, and as I know that my maximum limit is this one, so 10 times of the carrier signal. So that is my limit, right? So that by 2, and then I can say that it is ranging up to that again, but it is plus range, right? And then I am adding something like this. I will say that I have 2 cycles per sorry, I always forget the spelling of this one. Okay, I have this one. Oh, sorry, not this one. I I have to use this one again, because I have to make a very small offset. This divided by this small offset, which is t transmitted. So the signal which has been transmitted, so the length of that one. So I have to make it a very small, because let me actually, if you compare this one with this one, they are quite similar. But this one, the t transmit, this one and this one is quite similar, but they are reciprocal. Plus, they are from minus fs by 2 to plus fs by 2. So you have to thoroughly see both of these. And so if you understood, I have given you some assignment, right, to check that part. And if you see if when you understand that part, then you should come and see why am I subtracting this part, and you will see some relationship there too. So I'm not going to explain you this one. So again, I think I should copy this one. I mean completely this one. So I'll roughly, it is starting from minus limit of that which we have defined, but half of that. Why half of that? Because it is going to plus half of that, right, which is this part. uh, yes, plus this part, which is going to plus this part, right? So starting from minus half of that to plus half of that, and the length of transmission means that whatever we are transmitting divided by this length, because we have in time domain defined this much length for that, so in frequency domain it should be the same length. And I'm subtracting 1 from here. Just think about it. I don't want to explain this one, so think about this one, and I'll ask you in the next level why I added this part here. And so I'll just give you a little clue about this one. Minus fs by 2 to plus fs by 2, and they are divided by t trans, but there is 0. And maybe because why I'm subtracting that, just see why it is done there. So can you just think about it and let me know in the next slide. So now as I told you, if you have to transform your signal into frequency domain, what you have to do, you have to transform it using the FFT, or you have to take the Fourier transform of the signal. So the FFT transform your time domain signal into the frequency domain signal. So what was your signal here? This was the transmit of the signal. And why I'm expressing it in the frequency domain? Because I want to see each and every component of the frequency, so that I can discard the irrelevant frequency and I only leave the relevant frequency. And this is how the filter does. And then I should say that this is my figure number 7, I think. Yeah, figure number 7. And after the figure number 7, let me plot it. So plot, this is my x-axis, which is from minus fs by 2 to plus fs by 2. And since I shifted it by half of this, right, so I should use a built-in function which is called Fft Shift. So Fft Shift means that it will take this transmitted signal and it will take the FFT of the transmitted signal, and it will shift it by half. It will align it with the axis that I have defined here. So I will just simply use the Fft Shift built-in function, and I will then say that it is f underscore tran. And then I should do again the same thing with the f underscore fric, comma, Fft Shift with the modulated signal, which is our transmitted signal. So I want to visualize both of the transmitted and the received signal. So the transmitted was this one, and it is here, and I want to say that X label is my frequency and the Y label is my signal amplitude. So please remember, I haven't done the filtering yet. I just want to show you how the signal looks like, and the transmitted signal and the received signal, sorry, they have to be in the quotes. And then I will make it the legend, and the legend is the modulated signal and received signal. And received signal. So I think we can see it now. I hope no error. Yes. So this is how it looks like. I think I have done some mistake. Yeah, no, it's fine. It's fine. So you can see the received signal is very lower compared to the modulated signal. So the modulated signal was like this, and the received signal is very weak because at the receiver it is also it is um, mm, distorted, and there are many degrading phenomena happening to the signal. So let's recover the signal, and for that we have to do some filtering. We have to remove the unnecessary noise terms, which is because of the other frequencies. So I will say that f raise, for example, I'm calling it the f receive. So FRECE, let me make it a zero vector, so that it's a blank vector where we can keep the mm, yeah, where we can keep all the received answers. And what is this one? It should be equal to the sorry, are they are both similar, so it should be like this. And then FIR, this is a finite impulse response, and I'm putting some kind of um, here, let me show you. I'm putting some kind of constraint here. So I'm saying that any signal which is in this range from minus fs by 2 to plus fs by 2, if for example this is minus 3 times fs and this is plus 3 times fs, so any signal which is received, this is the concerned signal, this is my fundamental frequency, and any frequency which is happening at this side or at this side, I want to discard it. So to do that, or not even discarding, but at least I can reduce its amplitude. I will make its amplitude half of what there is. So even if there is some meaningful signal, it will not be completely eliminated, but at least its amplitude will be reduced. So I'll say that freq less than, for example, less than minus 3 time of fc, right? Or freq greater than 3 times of the fc, which I will simply copy and paste it here, and instead of less sign I'll put the greater sign, and I'll put the uh, positive sign there. So I always forget this semicolon. You should put it so that you don't see everything here. And then I'll simply say that f receive, which is I should say that this is frequency received. So I will say that f receive is equal to um, or f receive for the correct FIR, because this will gives me the index and the logical indices. Logical indices mean it will be either 0 or 1. So if they are 0, it will not consider it, but anything which is 1, it will only consider that one. So only consider the position which are positive, which are correct, and then what is f tran. So only take those signal, and from where take it, you have to take it from the FIR. So please think about it. Okay, it's not that complicated. You only have to see how are the logical indices works, and anything which is 1, it will be saved in this one. And if it is not 1, if it is, for example, I'll just simply copy it again, and I will paste it. So if it is not within this range, if it is not within the range I defined in line number 109, then I will say that not and not. If it is not, then reduce its amplitude, which means that filter out that part. So minus make it half. Okay, so the amplitude will become half, and then I will say that T-res. So I'll take the inverse Fourier transform to reconvert it from frequency domain into the time domain. And now let me plot it. So this is the figure number 8, and after the figure number 8 I will plot what to plot. T trans, which is this one. I think T underscore TRANS, sorry, T underscore TRAN, comma T res, which is this one, and then grid on, and also X label. And X label is now time. So we converted back from the time domain into frequency domain after removal of the noise terms. So this is time, and Y label is your received signal. So Y LABEL is your received signal. Signal, and yeah, I don't have to write the title, just let's see what's there. Oops, there are problems. Oh, 0. So I think I declared at the line number 3 zeros. This is why I defined it should be only 1, and also it should be 1. Again, and it is not 0, it is zeros. So this is the signal which has been received, and if you look at this one, this is received after we filter it. So we should probably compare it. Can you compare it with the AWGN and then see that how much filtering happened, and or do one more thing. First plot the modulated signal, then plot the received, the AWGN signal, and finally plot 2 cycles of this one and see how much degradation, how much you improve the signal. So it will be better if you do some practice like that. I'll upload this code, this source code, and also the slides and this video to your iClass. And please do all the assignments that I have given you today. So it's not the assignment to be submitted, but the next lab when you are coming, I'll be asking questions randomly from any one of you. So you should be very clear for every variable or everything that we have done so far. And please remember that in the midterm, almost 20% will be coming from the lab. So don't just ignore the lab. You have to do some practice on it. And if you have any question related to the lab, you can ask me in the lab or just an email. So that's all for today, and I'll see you next week. Thank you. Bye bye.